Okay, getting back to our discussion of events. We're going to talk now for a little bit about uh, not just how to put events together to make new events, which we did earlier, but what can we say about the probabilities of those new events that we get after putting them together in new ways. So one of the first questions you might be interested in is, if we take the first operation, the union, what could we say about the probability of the union of two events? And your first gut reaction might be to say, well, since you're putting things together, that's kind of like adding something. Why don't we just add the probabilities together? But there's a little problem with that. If you look at this picture here, you should see why that's going to be a problem. Here's a Venn diagram with E and F events. And you can see the Venn diagram's made up of the four regions. Everything in E but not in F, F but not in E, E and F, and then in neither. So if you were to add the probabilities of E and F together, and this is a little bit hand wavy here, but I think you get the sense of kind of where the argument's going. But if you add the probability of E and F together, you get probability of E would kind of consist of these first two regions here. And then probability F would get contributions from the second and third region. And if you add those two up, you get the first plus the second plus the second plus the third, which isn't quite what you want. E union F is just the first, second, and third. The problem is you've counted that second region twice, that part where they overlap. So what that means is, for our formula, we need to compensate for that. If you added something one too many times, subtract it off. And that's exactly what the formula says here. And if you remember about intersection, this second region here exactly is the region that corresponds to the intersection. So we get what's called the addition. Excuse me. Here what's called the addition rule. Probability of the union then is the probability of each of the individual events, but then you have to subtract off the probability of the intersection. So a couple comments about this. There's four terms here. So this means anytime you know any three of these terms, you can find the fourth one. So you don't have to use this just to find the probability of the union. You could use it to find the probability of the intersection, given the other three, or the probability of one of the events, given the other three terms. Now, it's true for any formula. You can do this. So it's not just something that it's not just something that's used just to find the probability of the union. Another comment, this is something, it's the first formulation of a whole much more general result called inclusion-exclusion. It tells you how to form, or how to count or find the probability of several different events. So say you had 3 or 4 or 12 different events. How would you find the probability of the union of those? It's a much more complicated problem, but it's answered in kind of the same way about you overcount things and you compensate for them, and overcount and compensate again. This is a really important formula that comes up in lots of different areas of math. Okay, well, there's a special case of this. So if the two events happen to be disjoint or mutually exclusive, they're called, which simply means that they have empty intersection. Their intersection is impossible. Then what's going to happen? Well, let's look at the formula. If E intersect F is impossible, the impossible event has probability 0. That's going to be 0. So the whole term just goes away, vanishes. So all we're left with is probability of E union F is probability E plus probability F. Very nice formula. Makes it very easy to find the probability of a union, but You can only use it when you know that they're disjoint. You already have to know that. So an example, and this one we don't know that they're disjoint because they're not. Select a card at random. So this is the E and F that we had before. So E was, I'm not going to go back, but E was the event selecting a heart. F was the event select a 7. The probability of selecting a heart was 13 out of 52. Probability of selecting a 7 is 4 out of 52. So to find the probability of selecting a heart or a 7, that's going to be 13 out of 52 plus 4 out of 52. But then we have to subtract off the intersection. So the intersection was the 7 of hearts, and that has probability 1 out of 52. So you have to subtract that off and get 16 out of 52, or 4/13. So the 7 of hearts got counted once in event E, and again in event F. So it got counted one more time than it should have, so we have to subtract that off. Okay. Now, a case where this wouldn't be the case, or the case where you could use the disjoint events, would be something, just to give you an example, find the probability of getting selecting a 7 or a 9. Now, those are disjoint events. If you select a card, you can't get a 7 and a 9 at the same time. You can only get one or the other, but not both. So in that case, the probability would be the 4 over 52 plus 4 over 52, and you don't have to worry about the intersection because they're disjoint. So that's a case where you could just use this simpler formula here. Another example. Oh, so we're going to talk about conditional probability. Okay. So this is supposed to say 4,000 students. So conditional probability is one of the most important ideas in probability and statistics. And it really helps to have a good feel for what it is and what it's saying. So I'm going to motivate this with a little example. I don't think it's good to just launch into the definition. But look at an example. Say you're at a high school, and there's a student body president election. And there's 4,000 students in the high school, 1,000 each year in school, freshman, sophomore, junior, senior. A little unrealistic, but makes the numbers work out nice. Let's say that 250 of the freshmen are going to vote for Jake. 25%. 450 of the sophomores, 45% will vote for Jake. 420 of the juniors, 480 of the seniors, 42 and 48%. Okay, so this is the situation. The whole student body broken up into 4 what we would call mutually exclusive and exhaustive categories, which is a fancy way of saying that everybody in the school is either freshman, sophomore, junior, and senior. And then the number out of each of those that would vote for Jake. And then I also expressed it as a percent. Okay, so that's the situation. So let's look a little closer at what's going on here. Let's say that we select a student, any student at random from the entire population. Okay, what's the probability that they'd vote for Jake? Well, 250 freshmen, 450 sophomores, 420 juniors, 480 seniors. So altogether that's 1,600 out of the 4,000 students. And if you add those all up, you should get 1,600. So that's 40%. If we think of this in terms of the long-term relative frequency interpretation, remembering that we're selecting a student at random, so they're all equally likely, then this is saying if you select a student at random over and over again, many, many times, about 40% of the time your randomly selected student will vote for Jake. And that's not really anything new going on here. Okay, now let's suppose in addition I tell you, what if I now tell you a senior was selected? So I go into the population, I select somebody at random. I don't tell you who they are. You can't see who they are. But I tell you, you know for certain that it's a senior. Say you can see their year in class, something by their student ID or something as their year in class, but you can't see their picture or anything. Is this going to change your mind about the probability? You still going to, if you had to make a bet, would you still rely on the 40%, or would you change it? Well, hopefully you would change it. Okay. Sure. Because now, let's go back and see. Now we're only looking at the seniors. You know it's a senior. And among the seniors, 48% of the seniors are going to vote for Jake, not the 40% of the entire student body. In other words, the probability now that you vote that the student is going to vote for Jake is now 480 out of 1,000, or 48%. Okay. So what have we really done here? What we did was we updated our probability based on new information. So this is really the ties in more with the Bayesian way of thinking about probability and statistics, that you have what's called a prior probability. You take in new data and you update the probability based on the new data. But the mathematical idea of conditional probability is completely valid and consistent with that in the frequentist terms of long-term relative frequency as well. So this event of being a senior, the fact that we knew somebody was a senior, that's what's called the conditioning event. Okay, and the event that we're trying to update our probability on, the probability changes, that's called the conditioned event. So the conditioned event here is voting for Jake, and the event that is conditioning voting for Jake is being a senior. Now, something to note about the numbers here. 480 out of 1,000. Secretly, so you got my advisor used to say that a lot, so I kind of picked it up. Secretly, 480 out of 1,000 is really 480 over 4,000 divided by 1,000 over 4,000. Now, it looks kind of strange to say that. What am I doing there? But it's true, right? I can divide the numerator and the denominator by 4,000. Why would I do that? Well, what's 480 out of 4,000? Well, that's the probability that somebody's a senior who votes for Jake. In other words, they're a senior and they vote for Jake. The 1,000 out of 4,000, that's the probability that I select somebody who's just a senior. In other words, the probability, if I tell you they're a senior, the probability that they vote for Jake now is the probability that they're a senior and they vote for Jake divided by the probability they're a senior. Because I can divide the top and the bottom by 4,000, which is the total number of outcomes, total number of students that we could have selected. So this example is the whole idea behind motivating the definition of conditional probability that I'll give you right now. So here's the definition. So suppose E and F are events in a sample space, and suppose the probability of F is not zero. That's really important. You have to have the probability of F be non-zero. The conditional probability of E given F, which we write E with this vertical line F, probability E given F, is the probability of the intersection of the two events, probability E intersect F, divided by probability F. Notice if you let E be vote for Jake, and you let F be select a senior, that's exactly what we did here. This is exactly the probability of the intersection divided by the probability of F. So that's the mathematical definition. Now, then we can say, okay, what can we do with the mathematical definition, to prove stuff with it and get nice results? But you really need to have this understanding of it on some level beyond just memorizing the definition. And that's what I tried to do in the previous example here. So we're going to pick up more with conditional probability in the next video.